everyone, welcome back to the Internet Report, where we uncover what's working and what's breaking on the internet, and why. This week we're examining how AI workloads are changing internet infrastructure and how NetOps teams need to prepare for this rapidly evolving future. I'm Barry Collins, and I'll be hosting today with the amazing Mike Hicks, Principal Solutions Analyst at Cisco ThousandEyes. As always, we've included chapters in the episode description below, so you can skip ahead to the sections that are most interesting to you. And if you haven't already, we'd love you to take a moment to give us a follow over at Spotify, Apple Podcasts, or wherever you like to listen. We're seeing some major shifts in how internet infrastructure is built and operated. How is the infrastructure landscape changing, Mike?
So we're seeing an increase in demand for bandwidth, which is driven by AI workload requirements. So we think about how we need to deliver that bandwidth, those areas there. We're primarily going to come to do that from a fiber perspective. The rationale behind that is even if we wanted to go from a satellite point of view, we really can't accommodate that much bandwidth up there. So then what this has led to is the providers, the ISPs, the telcos, rolling out and investing in fiber infrastructures. And we've seen a number of these telcos invest quite heavily into this fiber infrastructure and start to roll out quite a lot. So the likes of Zayo sort of building 5,000 new fiber routes specifically to cater for these AI needs. Lumen have secured over $8 billion in connectivity contracts in 2024, and they've been partnering sort of the major companies such as Microsoft, AWS, and Meta to deliver this. And AT&T is actually investing $5.75 billion to acquire Lumen's fiber assets. All of this growth sort of reflects this infrastructure build out, and it's actually occurring quite rapidly. So we're constantly putting out new bandwidth there, but the demands that are being required because of these workloads, because of the enterprises, the organizations wanting this, means we're starting to really rapidly roll this out. There's also another constraint, and that is that the patterns and the requirements and how this AI needs to be served means that a centralized model itself really can't effectively accommodate that latency and bandwidth. We can't have one pipe in, one pipe out scenario.
There were reports of telcos converting legacy central offices and telephone exchanges into facilities that can serve AI workloads. How significant is this trend for internet infrastructure?
This actually goes a lot to sort of how we want to serve these models and aspects, requirements for data sovereignty, and also that performance, that latency requirements. So, sort of high performing environments there. Now, the telcos themselves have a lot of central offices, but they also have these telephone exchanges that were initially designed for voice services. And the advantage of these is they already have this fiber connection coming into them. So there's multiple ones, they're distributed. These are fairly large bricks and mortar buildings, already serviced by fibers that we can actually sort of repurpose effectively to do that. And also because of the locations of where they actually start to be able to serve this edge type of model as well. So this has been happening for a while, but now we're starting to see this accelerate, where providers are converting these sites into what they call integrated cloud nodes. This allows them to utilize these assets and then offer these edge areas already serviced by fiber. They have the pits and pipes coming into them, and they can start to integrate these into the overall backbone.
Does converting these old offices or exchanges help from a power perspective? We're often told how AI data centers put huge demands on power networks, but if these facilities already exist, it means there's no new demand on the grid, right?
Absolutely. These already had service by power. They already have these systems in place because of what they had to run. And you've also got to remember what they're actually doing. So if we start to think of some of the workloads we want to put on there, these are effectively smaller workloads. So we're not having this huge power generation or this huge power requirements from those, sort of domain-specific models or small language models that they're looking to sort of run these cloud areas on this environment there. But to your point, these already have the power infrastructure in place to sort of service them. We're not having to build new power plants, and we're not taking away from a centralized data center, which is already have sort of other workloads and power requirements.
Instead of hyperscalers dominating the industry, AI has created this need for telco connectivity again. How does this change the internet topology?
So it's kind of flipped a little bit there. So the hyperscalers sort of historically have built their own infrastructure. And they've got their own data centers. They have leases on undersea cables. Some have their own undersea cables themselves. But this requirement for the high bandwidth, and as you just mentioned, the power, outpaces their ability to sort of build infrastructure quickly enough. Now, if you think about all the data centers they have around the world, they're already serving applications. These aren't sort of greenfield sites where they can automatically just go, we're going to hive off half of that to service these AI workloads. And then they can't build the infrastructure quick enough to be able to sort of service that. So then there's a shift back effectively where they were owning the entire service. They're starting to see this sort of shift where the telecommunication carriers themselves are sort of providing this connectivity in. So we're sort of shifting back to there, and we're then coming into these other data centers themselves. So we're moving effectively from what was a centralized hub and spoke, although we're talking about multiple data centers, it was still coming into a hyperscaler itself, to a more distributed, like complete mesh technology. This sort of increases the resilience in the internet by decentralizing the resources. Now, I know we had different availability zones and sort of failover sites, but we're sort of having more and more distributed architecture, basically.
So it's a step back towards the early days of the internet where everything was much more distributed.
It is. It's going back, it's like, I mean, again, we've talked about this. I'm very old. So I've come from the days of mainframe where everything was centralized. Then we actually moved out to the edge compute. We again came back to a centralized model, although it was distributed. And I know it sounds a bit strange, but yeah, we're coming out to now where we have these different areas of responsibility. But again, remember what we're doing is we're just expanding on distributed architecture. The whole hyperscalers and the cloud allowed the applications to accelerate on what we could deliver. But then there was a need to sort of have some of that distributed around the edge. All we've done is we've taken that one step further. We've moved more of the intelligence, as it were, the workloads, the IO workloads, more and more to the edge, and then had these multiple POPs, as it were, these data centers providing some of the bare metal.
We're hearing about these Neoclouds, AI-focused data centers being built in more regional and rural areas, rather than the traditional metro hubs. What does this mean for internet routing?
IO workloads require a significant amount of electricity. And this has prompted this construction of these Neoclouds near power sources rather than where we'd have the normal population centers. The obvious reasons: we don't want to be taking power from the grid. We don't necessarily have to be building new generations in the middle of a metro area. And remembering where the data centers are specifically, they were there to sort of serve the users. We wanted to have them close to the user population. So we started to see them move out to these areas because, one, we have space to be able to do it, satisfy these heat requirements. And then we also can have the sort of power plants and electricity sort of dedicated to that area. It's almost, if you like, a specific AI data center itself. There's actually sort of two distinct deployment models, and they serve different purposes. So we have these large central facilities, which are built into remote areas, sort of access to cheap power. They have to have cooling as well. And these handle the massive AI training workloads where immediate response time is less critical. We're still talking the magnitude of seconds or milliseconds there. We then also have, which is where we're talking about repurposing the telco facilities, we have edge micro data centers. Now, these are smaller facilities, specifically for latency sensitive inference, where the speed is sort of crucial. And therefore, then we need to put all these two together. So they all need to be connected with sort of high capacity fiber. So we need to be able to understand where the workloads are. We have obviously data sovereignty types of issues where we're running from a local perspective, when we want to be pulled from a deep research or sort of information from a larger model in the back end or some sort of learning in that area there. These all need to be linked together and sort of have this complex network or this multi-mesh of network where we need to be able to get across the two. So that's why we're seeing this increase in fiber as they've been sort of rolled out to supplement or to serve these data centers to make sure that they can actually communicate to each other.
Tell us more about these Neoclouds. How does their approach differ from the hyperscalers?
So they're altering the service a little bit because they're delivering what we call bare metal GPU access. So what we mean by that is effectively we're not buying an overall service. So where we might actually go into an organization, we'd buy a service that consists of multiple systems. Organizations can actually go and then just buy sort of time on these bare metal GPUs. So they're actually buying access where they can actually run their model from a specialized provider, the likes of CoreWeave or Lambda Labs. So these Neoclouds, because of their offering bare metal, not its comprehensive service, they can predominantly offer sort of a lower costs because they're being served by these fibers and we're not competing with other loads. They have the potentially faster access to the latest hardware than traditionally we would do from a hyperscaler. Now, the reason they're able to do that is because they are focusing solely on the compute and they're partnering with the telcos for the connectivity themselves. This allows for a separation where we're sort of moving towards this best of breed model. So rather than going and buying a complete service, they're actually buying, we're going to take our GPU from here. We're going to have a particular connectivity from here. We're able to have this best of breed model rather than the one-stop shop approach. Now, sort of building onto that, what that then allows them effectively to be able to do is to deliver anything as a service types of functionality.
So how are the hyperscalers adapting to this more distributed internet infrastructure model? What should we be watching for as these infrastructure trends accelerate?
So the hyperscalers are sort of shifting. So they're shifting to becoming customers in this ecosystem instead of sort of trying to own everything and offer things as a service. So they're actually looking to partner with and utilize some of this space on the GPU, as well as effectively using some of their models. So some of their systems, again, you could actually use that and actually put that onto your own environment yourself. So when your model is actually learning, you actually just purchase that model and using it there. So effectively then the hyperscalers become a customer of those. This extends into how they partner then with the telcos. So they're now buying connectivity services into these Neoclouds, into these facilities themselves. And then we're starting to see a sort of increase in AI infrastructure itself. The key concern for all of this is that what we're starting to do is to effectively create these potential new points of failure. Because we have sort of more interconnected systems, we're increasing this web. We have a greater distribution. If we're thinking about some of the edge compute as well as then sort of the large data center stuff, all of a sudden we have more interconnectivities. And even from a centralized system, we have more dependencies themselves. So we might have had a potentially sort of single points of failure where we're going to some authentication aspect or even some quota level or something like that, which is actually sort of some sort of gating factor. Now we've actually increased the potential for those single points of failure because I have more and more moving parts that all need to interact together. And I also don't necessarily know when they're going to need to interact together. I might be calling a specific model at one time or a particular tool at one area, creating a dynamic path. So I've always got to have that always on, and I have always these different connectivity paths in place. It's like the picking up the phone receiver. When I pick the phone receiver up, I expect, and I'm showing my age here, I expect to have a dial tone. It's too late if that dial tone's not there to actually then report the fault. And then what we've done now is we've effectively created this entire mesh where I need to have this global connectivity almost at all times so that I can guarantee that every time we actually need to call a service is going to be there.
So from a NetOps team's perspective, having a clear view of how all those different things are connected is even more important than it was before.
It is. And remember, a lot of this is going to be dynamic. So I don't know where I'm going to connect to. So it's very similar, again, going back to my telephone analogy of when I'm actually making a connectivity from a UCaaS type of service. I don't necessarily know which server I'm going to connect to, depending on where I'm making the call for those things. So any one of these paths at any one time could go any direction. So I need to understand all the components that are in there. But it also starts to introduce other aspects of that. We're crossing potential boundaries, where I'm actually getting that model served from, what data is available within that model, where am I running my model, and all these aspects need to be taking place. So I need to understand, yes, how my components are there, not necessarily how they're linked together, but how they interact together, and also where. So, where is that path going from a sovereignty perspective, a security perspective, but also from this aspect of speed. We have this concept of the edge compute to sort of speed that up there. If I'm having to retrieve something from an AI workload that is the other side of the planet, then that's going to increase and add some sort of significant latency into that.
Finally, Mike, what are your key takeaways about how this infrastructure shift might change how the internet works for everybody?
So the biggest change is that the internet is becoming more distributed and specialized again. So it's actually closer to its original design principles. But instead of everything flowing through massive hubs where we had these sort of centralized hubs, we're now seeing the compute and data processing happen closer to where it's needed, as well as requirements to come back to a centralized point or multiple centralized points, if that makes any sense, where we have to have this interaction together. So this should mean better performance for the end user, but actually overall a more resilient infrastructure because we have these multiple fibers, we have these paths coming in place, we have everything around there. But we also have this potential for more single points of failure because I have distributed systems upon distributed systems. We're not talking about a single architecture. We're talking about architectures that need to mesh together to be able to operate. And these architectures can potentially be spun up dynamically or be requested dynamically. So because of this is there, we therefore have more providers involved. We have more interconnections and more potential areas for optimization, but also more potential areas for degradation. We could lose a single part of that and it starts to have some performance degradation itself. So the key point to that is the organizations that understand how to manage performance and visibility across this distributed model are going to have a significant advantage. So essentially the internet is getting smarter, but it's also getting more complicated.
And that's our show. Please give us a follow and leave us a review on your favourite podcast platform. We really appreciate it. And not only does this ensure you're in the know when a new episode is published, It also helps us to shape the show for you. You can follow us on LinkedIn or X at ThousandEyes, or send questions and feedback to internetreport@thousandeyes.com. Until next time, goodbye.